Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Now, first for a question from Simon. He says, does water change the direction it swirls around the plug hole depending on which part of the world you're in?
Okay, this is quite an old chestnut. There is an effect there, and if you had a sink about, sort of 100 metres across, in fact, people have done it with sinks sort of maybe about the size of a room, perfectly circular with a very small plug hole in the middle, left it there for a fortnight, and then pulled the plug out, then it will tend to swirl in one direction in the north. It should swirl anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. Basically, because the Earth is spinning, then everything on top of it is spinning as well with it. So that the stuff at the sort of north end of it is going to be going slightly slower than the stuff. So if something moves northwards, because things at the south end are moving faster because the Earth is spinning, and it's further away from the centre of the Earth, the axis of the Earth where it's spinning, it's going slightly faster because things at the equator are going faster than things at the North Pole. So the south end's going slightly faster, the north end's going slightly slower. So when they move towards the centre, the south side's going to tend to overtake and the north side's going to undertake, and it's going to make things to start to spin. Now that is an effect, and it does exist. And it definitely exists with things like cyclones, so low-pressure areas in the northern hemisphere, they spin anti-clockwise, in the southern hemisphere, they spin clockwise. But they're really big. But when you get down to the size of a normal bathroom sink, the effect is so tiny that just how exactly you poured the water in, even if it was a day ago, there's still enough kind of swirl in the water to overcome this effect. Or if the tap's on one side so it goes in swirling, or if you put your hand in and swirled it around when you're in the bath, that will have a much, much bigger effect than what's called the Coriolis force, which is what should be making it spin in one direction or the other.
Thank you very much, Dr. Dave. Now then, hello to Tesco Tom, who says, why is it that mobile phones get no signal in underground car parks?
It's all to do with how the signal gets to the mobile phone. They're basically, the information travels in microwaves, so basically it's a bit like flashing a light. Morse code, you can send information with Morse code by flashing a light, and you could send messages that way. Mobile phones do it in a similar way, but with microwaves, which are a similar kind of thing to light and radio waves, but somewhere in between. They've got a wavelength of a couple of centimetres. And they basically just don't go through rock very well. They go through air okay, but they won't go through rock. So if you're underground, you've got 100 yards of rock over your head. The microwave just can't get through. They definitely won't go through metal. Metal will screen them very well. So if you're in a building with lots of metal around you, you'll get a very weak signal. Which is a good thing, because your microwave oven, which is cooking your food in your kitchen, you don't want the microwave to get out and cook you, so metal's very good at keeping it in. So basically the microwaves can't get through the rock, so you can't get the signal through. In general, the longer the wavelength, the better it will go through things like rock. So you may have noticed with FM signals, they won't go very far around the Earth, and if you get behind a hill, it tends to disappear. But if you're using medium wave or long wave, which are much longer wavelengths, then it tends to go round corners better.
Yeah, they bounce.
And it'll go through the rock slightly better. So if you're in the bottom of a valley, you might be able to pick up a long wave radio station, but not a VHF FM one.
All right. We've got Bernie on the phone. Hello, Bernie.
Hello.
How are you?
Oh, feeling a bit better.
Oh, good. You're through to Dr. Dave.
Quite a simple one, really. You look up in the sky and you see all these stars.
Yeah.
Millions of miles away. And the light travelling from the stars to Earth, does it degrade? And if so, how much?
By degrade, what do you mean?
Well, does some of that light get lost on the way? In those, say, 4 million...
A bit will do. I mean, if it goes through a dust cloud or a gas cloud, then that will absorb some of the light.
Yeah.
But the fact that we can see them means that not that much of it has got lost. I mean, normally if there's a dust cloud in the way, then you can't really see the stuff behind it particularly. What does happen to light if it's come from a very, very long distance away, which means a very long time ago, because it's taken a long time to travel to us, is that because the universe has expanded in that time, the light has also been stretched.
Stretched?
So it sort of gets stretched. So the wavelength, originally it was shorter, so the bluer end, and then as it travels and the universe sort of stretches, then it gets redder and redder and redder, which is called the redshift. And the further away we look, the more redshifted everything is, because the universe is expanding. And if you look right, the furthest back, which we can go to, which is very soon after the Big Bang, what's called the cosmic microwave background radiation. This is, if you look up in the sky, you see sort of microwaves, very cold, low-energy cold microwaves coming at you from all directions. But originally, those were X-rays. X-rays or gamma rays. And the universe has expanded so much by sort of billions and billions of times, they've been stretched all the way to microwaves.
Amazing.
So I'm not sure if that's quite degrading, but it's definitely it does change over a long time as the universe expands.
It's just amazing to me that you can look up in the sky and see sort of light from stars that it left them the time Victoria was on the throne or something like that.
Long before that. If you can look up into the sky and see light from galaxies which were there before, which left before the Earth actually existed.
Good grief.
Mind-blowing, isn't it?
Yes, it gives my brain cell an exercise just even trying to think about it.
Bernie, thank you very much indeed.
Okay, cheers.
Thank you. Mike in Colchester says he's heard that the real reason passengers are told to turn off mobile phones on planes is not safety, but because thousands of mobile phones in on mode, flying at low altitude, would mess up the mobile phone transmitters below. Is that correct, Dave?
I don't know if it's the real reason. I mean, there was definitely a big worry that mobile phones originally could interfere with sort of navigation systems on planes, which, if you're high up and you've got lots of time to deal with it, wouldn't be a problem. If you're low down, that could be a problem. I think all planes which have been built kind of since the advent of mobile phones have kind of pretty much been designed to take the radiation which mobile phones will give out, the microwaves which mobile phones will give out. But a lot of our planes are still 30, 40 years old, so you're not quite sure how they're going to behave in every situation if you didn't design them to be able to cope with it.
Nothing worse than being on a plane and somebody being on the phone.
And it would be very, very annoying. But there is a big issue with mobile phones interfering with mobile phone masts on the ground. Because essentially, sort of mobile phones, they use up a sort of a frequency. If they're transmitting, they'll use up a bit of a frequency. And if you're down on the ground, it only uses up that frequency for basically how far you can see, because the mobile phone's pretty much go in a straight line. They'll go through sort of small buildings and things, but not through any rocks. So it's about as far as you can see. So maybe only a few, 5 or 6 miles, you use up that kind of frequency space, roughly, approximately sort of concept. But if you fly up on a plane, your horizon is 100 miles or so. So you can use that frequency space and cause interference on that frequency over most of Britain at once. And so if you have 1,000 mobile phones up in planes, you could kind of cause serious problems for the whole mobile phone network.
Yeah, I think they should be taken and confiscated as you get on and off the plane. Dennis is in Cambridge. Hello, Dennis.
Hello, Sue.
Hi. Now then, what's your question about Dr. Dave?
Good evening, Dr. Dave.
Good evening.
I'm very much interested in these commercial satellite navigation gadgets.
Yeah.
I'm interested in how they work. And what intrigues me most of all is how good they are. I mean, they're accurate within about a metre or two, aren't they? Do they communicate with a computer on Earth?
The way they work is the Americans have put up a whole series of satellites which orbit the Earth. Yeah. There's, I don't know, there's somewhere between 10 or 20 of them at least.
Yeah.
They're orbiting quite low. They've worked out, they know their orbits very, very accurately. And these basically send out timing signals. So they'll send out a code, and then it's a whole series of pulses. It's actually quite complicated as to how they build the pulses so you can work out exactly where you are.
Yeah.
Because the time these radio pulses take to get from the satellite to you will be different depending on how far the satellite is away, because the signal travels at the speed of light.
Yeah, yeah.
If all of the satellites sent out a pulse exactly the same time, you can measure the difference in time between all the different satellites. And from that, you can work out the difference in distance between all the satellites. And then you can kind of do the sort of the plotting. It does the plotting in the computer, and it can work out where you are.
Where is the computer then, Dr. Dave?
There is a computer inside the Sat-Nav.
Oh, I see. So the satellites can absorb all the detail they need.
The satellites are just transmitting to you. They're transmitting. They basically send a pulse every kind of probably billionth of a second.
Yeah.
And a slightly different one every millionth of a second or whatever, so that each time you get one of these pulses, you can work out when it was sent from this satellite and which satellite sent it.
Yeah, I see.
Then the little computer inside your Sat-Nav system listens for all the different pulses coming from all different satellites, and it measures the difference in time between them. Yeah. So if one's a long way away and one's close, you can work out the distances between them, and you can work out where you are from those distances.
So are the maps stored inside the Sat-Nav itself then?
Yeah, and then the map is stored inside the Sat-Nav. The GPS, which is a positioning system, just works out where you are, and then you have a map inside the Sat-Nav, which is sold to you with the Sat-Nav inside the computer, the Sat-Nav of the whole country, and then it just plots where you are on top of that map.
Thank you very much indeed.
Thank you, Dennis. Thank
you.
Bye-bye.
Bye.
Now, there's a fantastic question in here from Gus in Little Bassingham. He sent an email. For some time now, many climatologists have suggested that there is a definite causal link between the warming up of the Earth's atmosphere and the emissions of CO2. However, the average global temperature between 1940 and 1975 decreased, while CO2 concentrations during the same period increased rapidly. Therefore, is it not safe to assume that any computer models combining these linked phenomena will invariably predict different forecasts of climate change according to which data is used? And in reality, most of the current warming is more likely to be linked to natural causes such as weather pattern cycles and variations in solar activity. And that's mankind's contribution to this change is either insignificant or only marginal. Gus asked this because under the Manhattan Declaration of March the 4th, 2008, 500 scientists, economists, policymakers and business leaders declared global warming is not a global crisis and recommended that all taxes, regulations and other interventions intended to reduce emissions of CO2 be abandoned forthwith. That's what he's put there. I have no proof that that is actually so. So we're taking what Gus has found looking at that, and he's obviously very interested.
Temperature has gone up and down. It does naturally go up and down. 10,000 years ago, the temperature here was like somewhere in North Sweden, and the temperature has been rising. It was naturally cold sort of during the 18th, 17th, 18th, 19th centuries, when they were having sort of ice parties on the Thames. The Thames would freeze so hard that you could go and light bonfires on it and they wouldn't burn through. But we are fairly sure that carbon dioxide will warm up the world. The bit between 1945 and 1975 is quite interesting because I think that was quite related to other kinds of pollution we were giving out. Because when we're burning lots and lots of coal, that releases lots of sulphur. And sulphur, when it comes out the chimney, tends to form little tiny, minute particles. And some of them kind of stay low and get caught by rain and create acid rain and kill forests in Sweden, although possibly not as much as we thought they did. And others get lifted really high up into the atmosphere and they reflect the sun and they actually cool the world. But since we've stopped burning as much coal and been burning much cleaner fuels, this kind of masking effect, which is cooling the world slightly, has been overwhelmed by the bigger underlying effect of the carbon dioxide warming it up. I mean, there is still a bit of an argument as to how much of the warming was due to the carbon dioxide, how much of it is possibly due to a bit of a natural warm-up going on anyway. I think scientists are fairly sure that if you carry on burning carbon dioxide, the world is going to get warmer because even if now it's not necessarily all of the effect, if you burn 10 times more carbon dioxide, you are going to create a problem, whatever happens. I personally think doing something about it is a good idea. Apart from anything else, if we keep on burning oil at the rate we are, we're going to run out of oil and we're going to have to find something to do with it. And I think there's also all sorts of other good reasons for trying to move away from fossil fuels, like we're starting to run out of them in nice, friendly countries, like Britain, America, and so most of them are now concentrated in the countries which have been so unstable no one's bothered trying to get them out of before. And there's lots in the Middle East and Russia, and there's some up in the Arctic. But I think people are fairly sure there has been an effect by now, and even if it's less than the natural effect, if we carry on at the rate we are going, it's going to have an effect and it is going to create huge problems.
Before, she was saying it was acid rain, then it was ozone, and now it's CO2 emissions. There are these buzzwords that carry through. And as the last line of what Gus has sent here, all taxes, regulations and other interventions intended to reduce emissions of CO2 to be abandoned forthwith. You know.
I mean, because the ozone thing basically, globally, I mean, that's actually one of the almost coming towards the success stories. Globally, we have incredibly cut down the production of the ozone-destroying chemicals. And the ozone hole still might be growing a little bit, but it's kind of starting to fluctuate, getting bigger and smaller. It's starting to level off the growth of it.
So we've managed to do something positive. That is fantastic. All right, we've got Maureen, who's on the telephone. Hello, Maureen.
Hello.
From Norwich.
Yes.
Your question to Dr. Dave is?
Well, My grandchildren asked me this the other day, and I didn't know the answer. They said, why can caterpillars eat stinging nettles and butterflies can land on stinging nettles and they don't get stung and we do?
I think the way a stinging nettle works is it's got lots of little tubes that are really sharp tubes, like hypodermic syringes, actually made out of silica, so they're made out of, it's the same sort of stuff as quartz.
Right.
And they're actually arranged around the outside edge of the leaf.
The outside edge, are they?
So,
right?
you know where the leaf has kind of got all these little kind of points?
Yes.
At the end of each of those points, there's a little kind of spike on it. It's a hypodermic syringe, and then if that jabs into you, it will inject some poison into you, and that's what causes the rash and why it hurts. And you can actually pick up stinging nettle leaves if you don't touch the edges. So you can kind of grab them and you can actually roll them into... Some people even eat them raw without stinging themselves, because if you roll them up into a ball with all the sharp bits pointing inward, then you can eat it and you can kind of break them up before they inject you, and it's not a problem. Apparently they've got quite a tangy flavour, because there's quite I think it's an acidic poison in them, and it actually makes them quite tangy. I've never tried eating them raw before. You can make tea out of them, and so as long as a caterpillar doesn't kind of crawl along the edge, which would be quite difficult, and if a butterfly will tend to land on the middle, it'll be fine. It's just if it kind of crashes into the side, it'd be a problem.
So they know if they avoid the edges, they'll be okay.
Yeah, and probably actually if you've got something as small as definitely a butterfly, it probably couldn't even hit them hard enough for it to go through, because butterflies have got quite a strong outer body, haven't they? The exoskeleton is quite strong.
So they could land on them and it wouldn't pierce them.
Even if they did, but mostly they're not going to land where the needles are.
Oh, thank you so much. I can explain that to them now.
Thank you, bye.
Bye.
Bye. Right, let's get back to these Sat-Navs then. Simon has picked up on the question. He's saying about how do the machines work regarding speed camera positions as his bleeps as a camera is approaching?
The old-fashioned ones, which were designed to try and stop you getting caught by speed cameras, the way especially the older speed cameras work is they send out a microwave beam. There's a lot of microwaves today for some reason. Send a microwave beam towards your car. Then if it gets reflected off your car, if your car's moving towards it, the pitch, the wavelength of this microwave beam will get slightly shorter, in the same way as if a car's coming towards you, the pitch gets higher, then as it goes away from you, the pitch gets lower, which is an effect called the Doppler effect. So the wavelength, essentially the pitch of this microwave beam changes slightly, and from that change you can work out how fast your car was going. So the old-fashioned ones used to detect the microwaves, and so if they saw some microwaves up ahead, they'd say there's a speed camera about somewhere. The problem is that if you're not careful, by the time it notices the speed camera was coming up, you'd already been caught. I think the Sat-Nav ones he's talking about, I've definitely seen on some road maps these days, they've just got a map of all the speed cameras in the country. Yeah. So I think in your Sat-Nav, it's got a map inside it already, so it'd be very easy to just add positions of all the speed cameras in the country onto that map. Yeah. So if the computer inside your Sat-Nav works out that you're approaching a speed camera, it just tells it to bleep. So it's just, in the same way as it can have all of the petrol stations in the country drawn on it so you know where to go to get petrol, it can have all the speed cameras on.
I guess so. How much are we using as far as car emissions and electricity and planes? How worried should we be about all these things?
I think electricity that we use is about a third of all the energy we use. This is numbers off the top of my head. Yeah. I think they're quite rough. Transport maybe about another third, and then sort of heating and running houses and industry maybe somewhere sort of another third, but possibly transport a bit less than that. I think air flights at the moment are only a few %, but they're growing very, very rapidly. And if you kind of extrapolate the growth for another 20 years, then it will start being a really significant portion of the energy we're using.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.